Writing equation for the preparation of 2-propanol from propanone. Okay, so propanone has an ONE ending, which means ketone. So propane is 3 carbons. And the number 2 carbon, there's a double bond, there's a carbonyl group. Okay. Reduction by adding hydrogen. So we have CH3, C, CH3, and here's a double bond we're going to open up. So now it's a single bond, and we're going to add hydrogen to both sides of that single bond. The oxygen has one side, and this carbon has the other side. So that's what we've added. Okay, that is 2-propanol, like it says up here. 2-propanol for your acid. Is that a primary, secondary, or tertiary alcohol? What type of alcohol is that?
It's a secondary.
Secondary, perfect. That's a secondary alcohol because there's 2 carbons attached to the carbon with the OH group. Okay, like I said, ketones are going to produce a secondary alcohol. Aldehydes are going to produce a primary alcohol. Okay, and you can see right there, this is a ketone because here's your carbonyl group. You have a carbon on both sides of it. If it was an aldehyde, one of those would be hydrogen. Okay, so that's a ketone. This bond opens up, and hydrogen is going to attack this side and add itself and to this side. And that's exactly what it does here. Here's your hydrogen, and here's your other hydrogen that I've added to prepare a secondary alcohol as propanone. Okay. Reduction of butanone. Reduction means adding hydrogen. Butanone is 4 carbons. So CH3, C, double bond O, CH2, CH3, plus hydrogen. Okay. Why don't we have to call that 2-butanone? It's redundant. You could, because that's what it is, 2-butanone, but it's an ONE ending, which means it's a ketone, which means it has to be between 2 carbons. Whether they put on the second one or the third one, it's the exact same compound, just flip it around. So it's the same compound no matter which way I write it. So butanone is 2-butanone. Okay, we're going to add a hydrogen across that double bond. So we're going to open up the double bond. So CH3, there's our carbon with our oxygen. I open up the double bond now, and then CH2, CH3. Okay, and we're going to add a hydrogen to one side of the double bond and a hydrogen to the other side of the double bond. Okay, so what's the IUPAC name for the product formed? Anybody want to guess?
2-butanol.
Perfect. Exactly right. 2-butanol. Okay. You've got to put the 2 there because it could have been the number 1 position also for the alcohol. Butanol, OL ending. So it says you've got 4 carbons, single bonds. There's your ane. OLE is a OH group, alcohol, and it's at the number 2 position. Okay. That's what it looks like a little bit neater. Again, here's your carbonyl carbon. Okay. And this is a ketone. Okay. You can tell it's a ketone because it ends in ONE and because there's 2 carbon groups attached, 1 on each side. Okay. So since that's a ketone, it has to reduce to what kind of alcohol? Is this a primary, secondary, or tertiary alcohol that is produced?
Secondary.
Secondary. Okay. Here's your carbon with the OH group, and there's 2 carbons attached to it. Perfect. All right. Any questions on reduction of an aldehyde or ketone to produce an alcohol? Reduction means adding hydrogen. If you're reducing a ketone, you're going to form a secondary alcohol. If you're reducing a aldehyde, you're going to form a primary alcohol. All right, so dehydration. Dehydration means taking away water. So alcohols dehydrate with heat in the presence of a strong acid, like phosphoric acid or sulfuric acid. And they're going to produce an alkene. They're going to make a double bond. Okay. It's similar to an elimination reaction. We're eliminating water. We're losing H and OH. Okay. So a molecule loses atoms and ions from its structure in an elimination reaction. So you have H and OH are being eliminated. They're removed from adjacent carbon atoms to produce an alkene. It has to be carbon atoms that are next to each other. You can't pick a carbon with the OH group and then 3 carbons down, pick it down for hydrogen. They have to be adjacent. You're going to lose the OH group from one, and then an adjacent carbon has to lose the hydrogen. It has to be right next to it in the chain. Okay. The reversal hydration reaction forms an alcohol. That's what we were just doing. Okay. So okay. When it actually goes backwards, it forms the alcohol, in other words. So here we have our alcohol. Okay, here's our OH group. And we're going to remove an OH and then an H. And we have to remove the hydrogen from the carbon next to it. We can't pick a carbon down here on that R group. Okay, it has to be adjacent to it. These have to be right next to each other. Okay, and you can't remove the hydrogen from the same carbon. Because we're not going to use this hydrogen and take it off, or this one. Okay, it has to be on the adjacent carbon atom. So we take that hydrogen away, the electron swings up from here. Take this OH group away, the electron swings up to here, and that's what forms our double bond and the production of HOH, which is water. So we've taken in this case, it's a primary alcohol, added strong acid and heat, and we produced an alkene. Okay, you can see the OH and the H form your water. Take a look at a real example here. Okay, you have the 2 carbons. Again, we're going to remove an OH and an H. Okay, and it has to be on the adjacent carbon. The electrons from here swing in. The electron from here swings in. That creates your double bond. So you've eliminated water and you formed an alkene. So what's the IUPAC name of our reactant, what we're starting with? That's what a lot of you are going to use this weekend.
1-ethyl.
Not 1-ethyl. Remember, name the OH group too. You're half right.
Ethanol?
Perfect. Ethanol. 1-ethanol or ethanol. Okay. Ethanol is your alcohol. It's vodka, scotch, bourbon, whatever you guys want to drink. Okay. Made of ethanol. Okay. And what did it form? Name the product it formed.
Ethene?
Ethene. Perfect. That's how your exam is going to be written. A lot of your questions. Okay. I will give you a word question and you've got to convert it into chemistry for me. Okay. So ethanol, I will say if you have ethanol and you add a strong acid and heat, what is the product you will produce? Okay. Ethanol, it's an elimination reaction for water, and it produces ethene. Okay. So this alcohol, name the alcohol we're going to use in this one.
Propanol?
Propanol, perfect. Okay, it tells you pro is 3 carbons, AN is single bonds, OL is an alcohol. And it then specifies the number 1 position. That is perfect. And we're adding heat, so we're going to eliminate an H and an OH. So we're going to eliminate OH, Now, what carbon do I have to take the hydrogen from? Do I have to take it from number 1, number 2, or number 3? Which carbon is going to lose a hydrogen?
Number 3.
Not 3.
2.
2, it has to be adjacent to it. Remember, this OH group is attached to the number 3 carbon. You have to lose a hydrogen from the adjacent carbon. Okay, so it has to be number 2. It has to come from right here. Okay, and that gives you our CH3, CH, CH2 with our double bond, because these electrons swing into here, and these electrons swing from here to create the double bond. Remember, you have to lose, once you have your OH group, you have to lose it from an adjacent carbon. Now, if the OH group is in the center, you can have a major minor product, the same as we did before, which you get that example. There's not always even just one product. You got to remember, it can randomly come from either side. But in this case, the OH group has always been on the end, so it doesn't matter what, it's always gonna be the same compound it's producing. Zetesro, that's what we were just talking about. Okay, some alkyl dehydration reactions produce a mixture of products. If the OH group is in the center, it can produce a mixture of products because it can take from either carbon adjacent to it, to the right or to the left. So if it's not exactly symmetrical, it will produce a different product. And you're going to have major and minor. So as Zetesro states, an elimination reaction, the alkene with the greatest number of alkyl groups attached to the carbon atoms of double bond is the major product. Just like Markovnikov's rule, hydrogen likes hydrogen. In reduction reactions, carbon likes carbon. So you're going to, the one with the most carbons attached to the double bond is going to be the major product. Then we added hydrogen, hydrogen always look for other hydrogens. That was Markovnikov's rule. Now we're eliminating, we're doing the opposite. Okay, we're eliminating H and OH. So the most stable one, or the major product, is going to be the one that has the most carbon atoms attached to the double bond. Carbon likes carbon. So for the addition, it was hydrogen likes hydrogen. For reduction, for elimination, it's going to be carbon likes carbon. So here's our example. And everything's labeled here for you. Our OH group is in the center here. Okay, so this is 2-butanol. Okay, we eliminate that. Now, there's our OH group. We can take an H from an adjacent carbon or an adjacent carbon. So we can pull the H from either one of those. Does that make sense? Because once you take that OH group, we're going to have to lose another hydrogen. And it has to be an adjacent carbon, one that's next to it. So it could never be over here. Okay. Oh, shoot. I must have hit the button. Advance that. Let's go back to where we were. There we go. Okay. So for this carbon here, it could never be that one because it's not adjacent to the OH group. So the first time we're going to take the hydrogen from the left side, and this is what we get. On the bottom one, we're going to take the hydrogen off of the right side, and this is a product that we get. So if you look at the carbon groups attached to the double bond, okay. So here's our carbon to the double bond, right? Here we have a CH, we have a CH3 group here, and we have a CH3 group here attached to it. Those are both attached to the carbon of the double bond. On this one, here's our carbon of the double bond here, and our carbon of the double bond here. We have a CH2 group, we have a carbon group attached here, and that's it. The other ones are 2 hydrogens. So the top one has 2 alkyl groups, carbon groups. The bottom one has 1. So this is our major product. Carbon likes carbon for these elimination reactions. All right. So now we got the compound on the left. And let's see if anybody can name the one on the left. See if you remember anything from, yeah, it was yeah, it was on Tuesday. We did naming of alcohols. So who can name this compound on the left side here? No takers?
2-methyl-cyclohexanol.
Perfect. You got it. It's exactly right. You got a cyclical compound, 6 carbons, so it's cyclo. And there's 6 carbons in a circle. Hexane. Instead of the E, we have an OL because there's a hydrogen, there's an alcohol group attached. So it's hexanol. Okay. And whenever there's a cyclical compound, okay, the alcohol is always attached to number 1 carbon. So this carbon becomes number 1. So then it becomes number 2. So you have 2-methyl, because there's a methyl group attached. 2-methyl cyclohexanol. Okay, it tells you it's in a circle, 6 carbons, single bonds, alcohol. Number 1 position. At the number 2 position, there's a methyl group. That's it. So 2-methyl cyclohexanol. So here's our OH group. Now you have to realize there's 2 adjacent carbons. There's a carbon here and a carbon atom here. The double bond can form in either place. Everybody understand that it has to pull a hydrogen from the adjacent carbon. And if there's more than one, it's going to go after the other one also. So we get 2 products formed. Okay, we get this product here, and we get this product here. Okay. So what's the name of the top product? It would still be, we still have our methyl group. Okay. And it's still cyclohexane, cyclo, hex, and it's ENE ending because of double bond. Okay. And we can put a 1, it's 1-methyl, 1-cyclohexane. If you want to do it both, you could put it 1-methyl, 1-cyclohexane, or methyl cyclohexane. It's at the number 1 position. And the other one, what would the bottom one be named?
Methyl cyclohexene.
Perfect. 3-methyl cyclohexane. The methyl group is at number 3 because this is going to be your multiple bond takes precedence over anything unless there's a functional group. So that's number 1. Has to go through the double bond 2, and that's C. So it's 3-methyl cyclohexene or 3-methyl 1-cyclohexene. Either way is fine. Okay. Which one is the major product? The top one or the bottom one? Remember, carbon likes carbon. So which one has the most carbons attached to the double bond? Right there, right? Because this one only has hydrogens attached to this double bond. This is hydrogen, that's hydrogen, that's CH3 and hydrogen. So this one has an alkyl group attached. So that's your major product. Okay, major product and minor product. So she'll be able to figure out the reaction, tell me what they form, and then be able to name major and minor products. Okay. Predict the product of dehydration. Okay. What are the major and minor products when 3-methyl-2-butanol is dehydrated? Okay. First, I have to know what 3-methyl-2-butanol looks like. So 3-methyl-2-butanol. Butanol is 4 carbons. And 2-butanol. So butanol is an OH group at number 2. And 3-methyl. Yeah. That's only CH. And there's a CH3 group here. Okay. So that's just one hydrogen on the 3rd carbon, because CH3 is an attachment group to give you 4 bonds to that. So 3-methyl 2-butanol is dehydrated. It means you're going to lose water. Presence of an acid, and then heat. Okay. So we're going to lose the OH group. And then we're going to lose a hydrogen. Okay. It has to come from this carbon or this carbon. Okay. Can't come from the methyl group. It can't come from down behind that. It has to come from an adjacent carbon atom. So you're going to have 2 products. You're going to have CH3. Or actually, if we pull the hydrogen off that, it will be CH2, double bond. CH, single bond. CH, CH3, and CH3. That's a double bond going this direction. Okay, let's take the double bond to the other direction. We can go to the right. Okay, so we have CH3. And we're going to still lose the OH group, still CH. And it's going to be a double bond. Okay, and now the carbon is going to lose a hydrogen that was adjacent to it. And that's what you're going to end up with. Okay. If you look at that, everyone has 4 carbons, and there are 4 bonds to every carbon, which is what you have to have. So is the top one or the bottom one going to be the major or the minor product, or they're both 50-50? What do we got with this one? Anyone take a guess?
Bottom is major.
Perfect. Bottom one is a major product. Top one is the minor product. And that is due to the fact that there is this attachment on that carbon, whereas there's 2 hydrogens over here attached. That has 2 hydrogens. This only has 1 carbon there. This one has another methyl group attached to that carbon of the double bond. Remember, carbon likes carbon for elimination reactions. Okay. So the most alkyl groups attached to the carbon of the carbon atoms of the double bond is going to make that the major product. All right. So let me erase some of that so we can see it again. So in elimination reaction, what it says is the alkene with the greatest number of alkyl groups on the double bonded carbon is going to be the major product of the reaction. Let that catch up for a second. It's erasing things. I kind of wrote right over the explanation here. It's slowly getting rid of them. All right, so the Sells rule states, so in an elimination reaction, the alkene with the greatest number of alkyl groups, so it's going to be major and minor, the greater number of alkyl groups on the double bonded carbon, okay, is the major product. Okay, so here's our reaction. This is what we're starting with. Okay, this is 3-methyl 2-butanol. Add acid and heat, and you get one product here and the other product here. In the top product We took away this hydrogen here. Okay. The electron swung that way. On the bottom one, the electron swung that way. And we took away this one of the hydrogens from here. And you can see there's more alkyl groups attached. There's a CH3, there's a CH3, there's a CH3. Those are all attached to the carbons of the double bond. Here you have CH2, CH, one alkyl group attached. That way you have 3. Right? So this is your major product on the top. This is your minor product on the bottom. Okay. Write an equation showing dehydration of each of the following alcohols. If there are 2 possible alkene products, indicate which is a major product and which is a minor, or whether it's going to be 50-50. Could be either one of those. So this is ethanol. Let's take the dehydration of ethanol. Dehydration means removal of water. So we're going to dehydrate that. Acid plus heat. So you're going to end up with, let's see, let me write this out here like this. There's your CH3, CH2, and there was an OH here and an H here. That's what you're starting with, right? And we're going to eliminate H and OH from the adjacent carbon. So let's take those off. Okay. And the electrons from that O bond and from the hydrogen from the adjacent one is going to form a double bond there. Okay. Now, what if can it have another product formed? No. OH group is on the end. You only have 2 carbons there. OH group comes off of this one. H group comes off of this one. That's the only product you're going to form. You're only going to form ethene. Okay. So here's it written out. You can see a compound. You're going to lose this OH, and there's only one other carbon taken H from. So it has to come from here. And you're only going to get one product that way. Because there's no other, the only way those electrons can fold is to fold into this bond here between those carbons. Okay, it can't fold to the other side because there's no carbon on the other sides. Okay, there's no way it can go in that direction. So it can only go one way. So the only product you can form is ethene. Okay, let's do this one. This is 2-propanol. Okay, so if we lose the OH group, now we can lose a carbon from, sorry, not a carbon, but a hydrogen. We can lose a hydrogen from here, or we can lose a hydrogen from here. Okay, it can go either direction. Okay, so we pull one of those hydrogens off, we're going to end up with CH2 double bond CH, CH3. If you pull from the right side, we're going to have CH3, CH double bond CH2. Okay, that's what you're able to form. Now, do you have a major, minor? Do you have 50-50? What do we have?
50-50.
Nope. It's not major, minor either. It's a trick question. You only have one compound. Those are both the exact same thing. It's a symmetrical compound. If you name this compound here, it's called 1-propene. If I name this compound, what's it called? 1-propene, because you label it backwards. They're the exact same name. They're the exact same compound. On the top one, you just count from left to right, because that's what double bond is. On the bottom one, you count from right to left. That's what double bond is. All you do is take this one and flip it to the other side. You got the exact same compound. So you only have one compound being formed because this is symmetrical. It makes no difference. So it's not, and I guarantee you see on the exam, it's not 50-50. It's not major, minor. Okay, it's only one compound. Remember, those are your different choices, 3 different types: 50-50, major, minor, or the exact same compound, one compound. Okay, and you can see it being formed. So it doesn't matter which way those bonds go, the electrons go, the double bond is going to be the exact same compound no matter where they're at. It's going to form one propene. Does that make sense? Can I get a thumbs up or a yes or a nod or something?
Yes.
Okay. Make sure everybody's understanding it. Because it is a difficult concept. All right. This thing, what's this thing called? Who wants to take a crack at this one? How many carbons we got? 6 carbons. So 6 carbons, we have hex. And it's all single bonds, so hexane. And it's an OH group, so it's hexanol. Okay. And the OH group is at number, it's either number 4 or number 3. It's going to be number 3 because we go with the lowest possible number for our functional group. So there's 3 hexanol, and we have an attachment here. We have a methyl group, and it's at number 4. So 4 methyl, 3 hexanol. All right. So now let's choose a different color. Let's choose blue. See how it shows up. We're going to get rid of an OH group. Okay. Can I take a hydrogen? Where can I take a hydrogen from? If I gave you a test question and said, which carbon will lose a hydrogen after the OH group with the OH group? And I say 1, 2, 3, 4, 5, or 6. I can take a hydrogen from which carbons? What are my possible choices?
3 or 5.
You got it. Perfect. 3 or 5. Remember, it cannot be on the same one, and it has to be an adjacent carbon. So once I find my OH group, I cannot go to here. I cannot go to here. I cannot go over here. I have to go to an adjacent carbon. It has to sling down. That double bond has to go between those carbon atoms. So I can go one of 2 ways. I can take a carbon from number 3. I can take a carbon from the number 5 group here. Hydrogen. I keep saying carbon, sorry. Take a hydrogen off of there. Okay, so one of my products is going to be CH3, CH2, bonded to C, CH3, that's our methyl group, double bond, slings down here, C, H, CH2, CH3. That's swinging the double bond in this direction right here to the left. Let's swing it the other way. CH3, CH2, CH, CH3, CH, double bond, CH2, no, I'm sorry, CH. Okay, oops, come back, CH, CH3. Okay, so those are 2 products. Okay, just by swing the double bond in directions. I don't write really neat, so let's pull it up here. Oh, it says major minor on it, darn it. Oh well. All right, so we lost our OH group here, and a hydrogen from here, and a hydrogen from here. Okay, on our top one, here's our result. The hydrogen bond swung to the left. It was the bond came here to form a double bond to the left side here. So on this, we have a alkyl group here. We have an alkyl group here, and a hydrogen and an alkyl group here. We have 3 alkyl groups attached, 3 carbon groups. On the bottom one, the electron swung to the right-hand side, form the double bond. We have 1 alkyl group here attached to that carbon, and we have 1 here. So I have 2 alkyl groups on the bottom attached to the carbons of double bond. I have 3 alkyl groups attached to the carbons of double bond on the top. So the top is my major product. The bottom is my minor product. Okay. What's that going to do? Okay, we're going to eliminate OH group. and we're going to eliminate a hydrogen. It could be from this one, or from this one. Is it going to matter which of those carbons I take the hydrogen from? Does that make any difference?
No.
That's perfect. No, it's gonna be the exact same product no matter what I end up with, because you have double bond attached there. So no matter which one I take it from, it's going to make no difference. Okay. So let's look at here. Again, we took the OH group and we pulled a hydrogen, say off of this one. So we have our CH3, and our C double bond CH2. It's going to be the same product. There's only be one product form, whether this folds down to here, folds down to here, or folds down to here for a double bond. We're going to the exact same product. Okay. It's always going to be 2-methyl, 1-propene. Because it's always going to have the double bond, the lowest possible number. So if you want to work it through, you can pull a hydrogen off of any one of those. You'll get the exact same product, no matter which carbon you take which hydrogen you take off of which carbon atom. Does everybody see? If you have a symmetrical compound, it's not going to make any difference. I mean, there's CH3 on each side of that. That's symmetrical. So no matter which one I take it from, it's going to be exactly the same. Oxidation reaction of alcohols. Okay, oxidation means adding oxygen, losing electrons, or increasing the number of bonds to oxygen in a compound. So going from an alcohol to a ketone. Okay, so alcohol would be ROH. A ketone would be RC, double bond O, another R. You've increased the bonds of the oxygen. Or going to carboxylic acid, RC, double bond O, OH. All those cases, we're increasing the amount of bonds to oxygen. That's oxidation, most in organic chemistry. Losing electron, we usually use mostly inorganic chemistry. It's easier to keep track of it this way. Okay. So alcohols may be oxidized with oxidizing agents to aldehydes, ketones, carboxylic acids. These are elimination reactions of 2 hydrogens. So we're pulling hydrogens off to increase the bond to oxygen. Okay. The most common used oxidative agent of basic potassium permanganate in a basic compound, OH. Okay, and chromic acid. Those are our 2 oxidizing agents. What cause oxidation? Okay, because they absorb electrons, and oxidation is the loss of electrons. So these become reduced. They're oxidizing agents. Okay, when we're doing organic chemistry, rather than keep track of it, we put this little O with brackets around it. When you see that, that means oxidation in organic chemistry. Okay, so it's a general oxidizing agent. Whether it's potassium permanganate, whether it's chromic acid, whatever we're using, it just means the compound is being oxidized. Okay, so here we have methanol. Okay, remember famous wood alcohol, extremely toxic. One of the things that causes you to go blind. Okay, we're going to oxidize it, which means you're going to increase the number of bonds to oxygen by reducing the amount of hydrogen. We're going to take 2 hydrogens off of this compound. We're going to take a hydrogen from the oxygen group, from the OH group, and we're going to pull a hydrogen off of that same carbon. Okay, so the double bond, the electrons from this hydrogen will go here, one of the electrons from this hydrogen bond will go here. So it'll create this double bond, and you still have these 2 hydrogens remaining. Okay, that's oxidation. You've increased the number of bonds to oxygen, or you increase the total amount of oxygen, one of those 2 things. So we went from methanol to methanal. Methanal, Al ending, is an aldehyde. Remember, aldehyde has a H attached to the carbonyl group. This happens to have 2 hydrogens attached. That's formaldehyde, which is also extremely toxic. Okay. Oxidation reactions of primary alcohols. primary alcohols have one carbon attached to the carbon with the OH group. That's the definition of a primary alcohol. Okay. They usually oxidize to carboxylic acids. Okay. So with some care, using CrO3 chromate as a reagent, an aldehyde may be obtained. So you can get an aldehyde produced from the alcohol. Okay. So this is a primary alcohol, right? This, how do we know it's a primary alcohol? Because here's the carbon with the OH group attached. There is one carbon alkyl group attached. So it is a primary alcohol. Okay. And again, oxidation reaction, here's a little O in our brackets, means we're going to lose a hydrogen from the OH group and a hydrogen from the same carbon. The bond here, one of the electrons from the bonds goes down here when it gets broken. One of the electrons from the bonds goes here when it gets broken, causing a double bond. And this produces an aldehyde. Okay. So primary alcohols oxidize to an aldehyde. Okay. Write equation of the oxidation of 2,2-dimethylpropanol to produce 2,2-dimethylpropanal. Okay. So you have to know what these are, right? So 2,2-dimethylpropanol. Propanol has 3 carbons. And let's see what we're at. 2,2-dimethylpropanol. So the propanol is on 1 carbon. So CH3, C, and propanol is CH, COH, CH, CH3, CH3. And we're going to oxidize it. Okay. So it's 2,2-dimethyl propanol, the OL group. So the alcohol's on the carbon. Okay. So is this a primary, secondary, or tertiary alcohol? What type is it?
Primary.
Primary. Got it. This is a primary alcohol because here's the carbon with the OH group attached. How many carbons are attached to that carbon? 1. That's primary. So the OH, we're going to take an OH and H here, and we're going to take an H from the same carbon. Okay. So the electrons from here slide into that bond, slide into that bond. Right. So we end up with CH3C. Here's our 2,2-dimethyl. Okay. Goes to our C, double bond O now, and our H goes in aldehyde. Okay. So here's it drawn out. This is our primary alcohol. Right down here. This is 2,2-dimethylpropanol. Okay. We're going to lose this hydrogen from the oxygen from the OH group, and we pick another hydrogen off the same carbon. So we'll lose this one. Could pick the top and the bottom, doesn't make a difference. So one of the electrons swings down here from that bond being broken. One of the electrons swings down here from that bond being broken. And what forms our carbonyl group with our hydrogen and the rest of our compound. And this is 2,2-dimethylpropanal. Has an Al ending because it's an aldehyde. Okay. So primary alcohols oxidize to form an aldehyde. Okay. Because it takes a hydrogen off the oxygen and a hydrogen off that same carbon. Okay, write an equation of the oxidation of the following primary alcohols to aldehydes and name the products and reactants. All right, so here's what we got. It says to name this thing. Who wants to take a stab at it? No takers?
3,3-dimethylbutanol.
Perfect. 3,3-dimethylbutanol. Okay, there's 4 carbons. Okay, you have 2 methyl groups attached at the number 3 position, so 3,3-dimethyl, and you have an OH group at the number 1 position. So it's butane, and it's all single bonds, so it's butanol and 3,3-dimethyl. Let me get rid of that from that section. All right, so this is oxidation. Oxygen brackets. And what's going to happen? We're going to take one of these hydrogen. It's going to form the bond there. And one of those hydrogens. So that hydrogen leaves. And one of the hydrogens from here leaves. Okay? And the electrons get shared and form a double bond to the oxygen. Okay? So here's your compound. You're going to lose this hydrogen and one of these hydrogen. And they're going to form the double bond right here. Okay? And you're going to end up with an aldehyde. And the name of the aldehyde, again, you get the lowest number to the carbon atom of the functional group. So it's still going to be 3,3-dimethyl butanal. So instead of the OL ending, we're going to have an AL ending. AL stands for aldehyde. OL stands for alcohol. That's the difference. Okay, so 3,3-dimethyl butanol, and then 3,3-dimethyl butanal. When you see that AL ending, you know it's an aldehyde. When you see that OL ending, you know it's an alcohol. The names are all going to tell you exactly what is in the name. So there's an AL ending. There's 4 carbons, single bonds. Okay, an aldehyde is always at the end, so it's always be in the number 1 position. You have to put a number there. And then it tells you there's 2 methyl groups attached. 3,3-dimethyl. At number 3 and number 3, there's 2 methyl groups. Okay. And our friend ethanol again. We're going to oxidize ethanol. This is what happens in your liver. It's not the ethanol that causes your hangover. It's the oxidation of it product. It's this aldehyde that makes you sicker than anything when you drink. The ethanol doesn't cause hangovers. The oxidation of it in the liver causes your hangovers. All right, so CH3O is ethanol, and we're going to oxidize it. And we're going to end up with CH3, and then we're going to pull a hydrogen off the OH group and a hydrogen off that same carbon. Okay, so ethanol oxidizes to, what's the name of the compound? If this is ethanol, this is what? What's an aldehyde ending?
Ethanal.
Ethanal. Perfect. You got it. Okay, again, we've lost this hydrogen, and we've lost one of these hydrogens. One of the electrons from that bond goes here, one electron bond goes here, forming a double bond, causing oxidation. And this is ethanal. So this is ethanol. This is ethanal. Aldehydes have an AL ending. Alcohols have an OL ending. Okay. Secondary alcohols. So primary alcohols oxidize to aldehydes. Secondary alcohols are connect differently because it limits the number of hydrogens we can take away. Secondary alcohols oxidize to ketones. So if it's a primary alcohol, it goes to an aldehyde. If it's a secondary alcohol, it oxidizes to a ketone because there's going to be another carbon group in the way there, which we'll show you. This is also the same reaction, elimination of 2 hydrogens, just like we did before. Oxidized agent is chromium 6. Tertiary alcohols do not oxidize. I guarantee on the exam, you'll see something that says give the oxidation of this alcohol, and it's going to be like 2. I think it was tertiary alcohol. I'm trying to think. 1,1-dimethyl ethanol. which is a tertiary alcohol. What's the oxidation product? And there is none. Tertiary alcohols do not oxidize. There's no hydrogen to take away. Remember, tertiary alcohol is going to be like CH3, 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 OH. That's a tertiary alcohol. So we take away this hydrogen, and there's no other hydrogen to take away. You can't do it. There's no other hydrogen attached to this carbon. So it's impossible to take two hydrogens away. So they don't oxidize. So primary alcohols oxidize to an aldehyde. Secondary alcohols oxidize to a ketone. Tertiary alcohols do not oxidize. There's no hydrogen to get it. It's impossible. You can't take it away if it's not there. All right, so here's our secondary alcohol, because we have two alcohols attached. That doesn't look good. We have one there and we have one there. Okay. So we remove this hydrogen. So its electrons swing to there. And remove another hydrogen that's on the same carbon as the OH group. And these electrons swing up to here. And that forms our carbonyl group. And now there's two R groups, or two alkyl groups, on the opposite sides of the carbonyl group. That's a ketone. And how we name ketones is ketones end in ONE. So alcohols end in OH, aldehydes end in AL, ketones end in ONE. That's it. That's the whole summary in a nutshell there. So write an equation of the oxidation of 2-propanol to produce propanone. Again, ONE ending, you know it's a ketone. 2-propanol, propane has 3 carbons. There's carbon. There's your H. There's your OH. Where am I at? 2-propanol, CH3. Okay. 2-propanol, 3 carbons, all single bonds, OH group attached to number 2 carbon. Okay. That is a secondary alcohol because there's 2 carbons. Okay, that's the carbon of the OH group attached to it. There's 2 carbons attached to that. That makes it a secondary carbon. So you know it's going to produce a ketone. Then we have our arrow, then we have our oxidation sign. Okay. So we're going to take away this hydrogen and this hydrogen. Hydrogen on the same carbon as the OH group. And the electrons are going to swing up to that bond to form a double bond. So you're going to have, as your product, CH3, C, double bond O, CH3, which is a ketone. You have your carbonyl group, and on both sides of it are R groups, and that is a ketone. And that's 3 carbons, and it's propanone, O-N-E ending. Okay. You don't need to say 2-propanone because there's no other place that oxygen could be. If it was on the end, it'd be an aldehyde, not a ketone. So it wouldn't be named as a ketone. So you don't, it doesn't have to be redundant. So you can just put propanone. So here's your compound. Here's 2-propanol. Okay. You're going to remove a hydrogen from the oxygen OH group and a hydrogen from the same carbon. The bonds from this group, the electron is going to swing there. One electron from this group can swing there. And you're going to form your carbonyl group, which is 2-propan or propanone. Okay. Again, if this hydrogen here were not present, no oxidation can occur. And that would make it tertiary alcohol. Okay, oxidation of the following secondary alcohol. Oxidize it. Okay. The name of that alcohol is 2-butanol. OL ending, all single bonds, 4 carbons, OH group in the number 2 position. So 2-butanol. Okay, oxidizes. What are you going to lose? You find your OH group and you remove one of the hydrogens. And we're going to remove another hydrogen on the same carbon. So it has to be this one. You cannot remove a hydrogen from here, or from here. When you're for oxidation, It has to come from the same carbon atom. Okay, so you do that, you're going to form CH3. C, again, you move those two H's, so you got double bonded oxygen. CH2, CH3. Okay, that is butanone. 4 carbons, single bonds, ketone. And again, at the number 2 position, you get to put 2-butanone. You don't have to, because if it was over here on this carbon here, it would still be 2-butanone. You flip it around, it's the same compound. And if it was on the other ones, it'd be an aldehyde, not a ketone. Okay, so you don't have to be redundant. So it's butanone. Okay. Again, here's your hydrogens. You're going to remove. They're going to form that carbonyl group by forming a double bond right there. And that's 2-butanol. That's your alcohol. And then this is 2-butanone or butanone. Either way, you put the 2 or not the 2, makes no difference. Okay. Okay. A common name you might see also is methyl ethyl ketone. If you see that, you know this, you know it's a ketone, so it's C double bond O, and a one group is methyl, one group is ethyl. It's very easy to do with those common names. So if you see the word ketone, you put a carbonyl group, and it tells you the 2 attachments. One's methyl, one's ethyl. All right. Now we got this monster here, and we're going to oxidize it. And what's going to happen? You should be getting the pattern by now. Okay. You find the OH group. You take the hydrogen off the OH group, and on that same carbon, you take away another hydrogen, because you're losing 2 hydrogens for elimination reaction. Okay. And the double bond is going to form between the carbon and that oxygen from the 1 electron from each bond when it was broken. So that's going to form CH3, C carbonyl group, CH2, CH2, CH3. Okay, so let's name this compound real quick here. Oops, here I come down. Let me grab my pen. All right, so how many carbons you got in a straight line? Someone should say 5, right? We have 5 carbons. Okay, so that's pentane. Okay, so it's a ketone, and the carbonyl group is at number 2. So it's 2 pentan, AN because it's all single bonds, and its own 2-pentanone. The common name would be methyl propyl ketone. A methyl group, a propyl group attached to a ketone. You might see that name also. Okay, so here's the hydrogen you took away. Remember, we find the OH, you take the hydrogen, and the hydrogen has to come from the same carbon that has the OH group. And it forms the carbonyl group, carbon double bond oxygen right there. Okay, this is 2-pentanol, that's the alcohol. And this one is 2-pentanone, O-N-E ending, okay, or methyl propyl ketone. Okay, it says you have a ketone, and it says on one side is a methyl group, another side is a propyl group. Here's your methyl group, there's your propyl group. Methyl means 1, propyl means 3 carbons. Good so far?
Yep.
All right. Tertiary alcohols cannot be oxidized. Don't make that mistake on the midterm. If you have a tertiary alcohol, it is not going to be oxidized because there is no hydrogen for it to be taken away. You take the hydrogen off the OH group, there's no other hydrogen attached to the same carbon, so you can't use it. Because here's 3 R groups. Okay, when you're doing an oxidation, you take away the hydrogen here, and you got to take away another hydrogen from the carbon on this attached to OH group. There is no hydrogen, so you can't do it. No reaction occurs. Okay, so no one should miss the oxidation of tertiary alcohols because it doesn't happen. For the oxidation reaction to occur, the carbon bearing the hydroxyl group, this carbon right here, okay, must contain at least one carbon hydrogen bond. This guy right here has to have a hydrogen attached. If not, it's not going to happen. There's going to be no oxidation to occur because you can't create a hydrogen where there isn't one. Okay. Tertiary alcohols contain 3 carbon-carbon bonds to the carbonyl carbon, where the OH group is. They cannot undergo oxidation. Cannot. So primary alcohols oxidize to aldehydes. Secondary alcohols oxidize to ketones. Tertiary alcohols do not oxidize, no reaction. Okay. Let's do this, then we'll take a little break. Use the IPACK nomenclature system to name the reactants and products for each of the reactions. Classify these as primary, secondary, tertiary, which alkenes can be cis or trans. Okay, let's go through an example here. This is hydration reaction. Remember hydration reactions?
Yeah.
Hydration means adding water, adding H and OH across a double bond. Okay, so we open this double bond up right here, and we're going to add OH and H, H and OH. Okay, so there's 2 products you can form. Put the OH on the second carbon or the OH on the first carbon. Okay. So this one is, you can see where that one's attached. The hydrogen was added to this carbon right here. And remember, when we're adding hydrogen, it's hydrogen likes hydrogen. So hydrogen is added here onto this side. There were 2 hydrogens here, 1 on this side. This is your major product. Remember Kolakow's rule, hydrogen likes hydrogen. Okay, the other one has a hydrogen added here. There was 1 other carbon here. So you ended up with H2, ended up with an H3. The H3 is going to be your major product. Okay, so you got to name these things. So this is propene, and propene has no cis trans isomers, right? Because you have CH3 bonded to CH, double bond, CH2. We have the same thing attached to that carbon. You could have no cis trans isomerism when you have the exact same thing attached, because it doesn't matter which way those flip. There cannot be a trans or a cis. Okay, so that was kind of a review of the different things we talked about with addition reactions of hydration. So we want to identify each of the compounds, what our major minor product is, and whether there's a cis trans isomer with it. All right, so we're starting with propene. Okay, this cannot have a cis trans isomer because there's 2 identical groups attached to the double bond. So no cis trans isomer is possible. We're adding water. We have an H and an OH. We have our OH over here and an H over here. Now when we're doing addition reactions with hydration, okay, we're gonna, the hydrogen likes hydrogen. So this one, hydrogen attached where there's 2 more. That's where the most hydrogen is. That's gonna be our major product. This hydrogen attached where there's only 1 hydrogen. That's the minor product. It wants to know whether there's a primary, secondary, or tertiary alcohol. Okay. On this one here, is this first one here on the top, the major product? Is that a primary, secondary, or tertiary alcohol? Which one would it be? This would be a secondary alcohol. There's 2 carbons attached to the carbon with the OH group. Okay, the minor product, which is propanol, 1 propanol. Would that be a primary, secondary, or tertiary alcohol?
Primary.
Primary, perfect. This is a primary alcohol. Okay, because there's only 1 carbon attached to the carbon with the OH group. Okay, do we put names on these? Yeah. So 2 propanol is your secondary alcohol. And this is propanol, which is your primary alcohol. Okay. Do the same thing again. Hydration reaction. Okay, of ethene. Now, can ethene be a cis trans isomer?
No.
No, perfect. Because your same group's attached on both sides of the carbon. There's no way to get cis trans isomer out of that. So we add water, we put OH on one side of the double bond, H on the other side, or switch it around. If we switch it around, it's going to be the exact same thing. You put HOH, it's just going to be the same compound, just flipped around in space. Okay, so we add an OH group to one side and an H to the other side. And we get ethanol. Now, is ethanol a primary, secondary, or tertiary alcohol?
Primary.
Primary. Perfect. Okay. So ethene, okay, no cis trans isomers, like we said. Okay. Ethanol is a product and it is a primary alcohol. So we create a primary alcohol by adding across a double bond. Okay. Here's another compound. We need to name this one. 1, 2, 3, 4, 5, 6 carbons. And the double bond's at number 3. So this would be 3-hexene. Okay. We open up that double bond. We put an OH on one side, an H on the other side. And this is completely symmetrical. Right? So it's only going to produce one product. No matter where I put the, or if I switch these around here, it's still going to produce the same product because it's the same on either side. Okay. So looking at the reactant, is cis trans isomer possible with the 3-hexene?
Yes.
Yes, it is. Perfect. Because you write it like this: CH3, CH2, CH, double bond, CH, CH2, CH3. There's your trans isomer. If I switch these around, that would be cis. So cis trans isomer is possible with this compound. And if we name the product, it would be 3-hexanol. All single bonds, 6 carbons. OL is an alcohol, which is an OH group at the number 3 carbon. 3-hexanol. And this one is a primary alcohol. Secondary, I'm sorry. Here's your carbon with the OH group attached. You have a carbon attached here, and a hydrogen. So you have 2 carbons and a hydrogen, 2 carbons attached. It's a secondary alcohol. Okay. Same thing. Do the same thing again. This is going to be a little different. We're going to add hydrogen instead of water, though. This is hydrogenation, not hydration. Okay. So how many? We have 4. This is aldehyde. Aldehyde is going to an alcohol by adding hydrogen, by reducing it. So again, we attack the double bond. The name of this compound is, there's 4 carbons, and it's an aldehyde. So it's bute-10-al. Okay. We're going to attack this double bond. It's going to open up. We're going to add a hydrogen to this side of it and a hydrogen to this side of it. Okay. And that's the only way we're going to get the only compound there formed. So we're going to have a CH2OH ending. And this compound is butanol, or 1-butanol. Okay. That's an alcohol. 4 carbons. All right, can this have, let's see, what else it wants to do? Provide the IUPAC name for each one. So butanol, 1-butanol. That looks like it. So it's butanol, goes to butanol, and it is a primary alcohol. Okay. This is the carbon with the OH group attached, and there's 1 other carbon attached. So that is a primary alcohol. Same thing here. This is a ketone because here's our carbonyl group and there's carbons on both sides of it. So it's a ketone. So there's 4 carbons and it's a ketone. So it's butane. Oh, all single bonds. And it's in the number 2 position. You can put 2-butanone or you just leave it as butanone. Either way is fine because it can't be anywhere else being a ketone. Okay. We're adding hydrogen across this double bond. We're going to open up this double bond right here between the carbon and oxygen, put an H on one end and H on the other end. Okay. And now we've got an alcohol. 4 carbons. We have got 2-butanol. Okay. Is 2-butanol a primary, secondary, or tertiary alcohol? Which one?
Secondary.
Secondary, perfect. That's exactly right. Make sure we're still recording here. Make sure everything's going. Yeah, it's still recording. It is a secondary alcohol. Perfect, because there's 2 carbons attached to the carbon with the OH group. So 2-butanone, and it produces 2-butanol, which is a secondary alcohol. Okay. And name the alcohol reactions through system, same principles here. And we are doing a reduction. We are doing a formation of an alkene. Okay. We're eliminating, this is a dehydration reaction. We're eliminating water from the compound. Okay. So we've got, where are we at? We're going to name these compounds. So the name of the first compound here, this is 3 carbons. Okay, you have 3 carbons in a single chain, OH group attached to the end of it. So this is pro, that's your 3 carbons, all single bonds, and ol, 1-propanol. Okay, remember dehydration reactions, we're going to lose an OH group, and we're going to lose a hydrogen from the adjacent carbon. In this case, there's only 1 adjacent carbon, that's right here. So we're going to lose a hydrogen from that side also. Okay, so you pull off 8, and that forms our water. It's a dehydration reaction. Okay, so that leaves us with the OH gone, and the electrons from that, breaking that bond form here, the electrons from this bond, when the hydrogen gets lost, forms that, and that forms your double bond. And that becomes propene. Okay. And it wants to know if 1-propanol, our starting product here, is this a primary, secondary, or tertiary alcohol?
Primary.
Primary. Only attached to 1 carbon. The carbon of the OH group is only attached to 1 carbon. So propanol, it's a primary alcohol, and propene is the product that was produced. Okay, again, dehydration reaction. We're going to lose OH, and we're going to lose H from either this carbon or this carbon. Now this thing's completely symmetrical. So it doesn't matter which carbon we pick. It's going to be the exact same product being formed. Okay. So the electrons from this bond, from this OH group, come down to, we go on this side, then the hydrogen from this side forms your double bond. Okay. And go the same way we went to the left side, the exact same product. So it makes no difference in this case. There's no major minor, there's no 50-50, there's just 1 product being formed. Okay, so the name of the reactant, we have an OH group in the number 2 position, and there's 3 carbons. So it's 2-propanol. Okay, is 2-propanol a primary, secondary, or tertiary alcohol?
Secondary.
Secondary, perfect. 2 carbons attached to it. And the name of this compound, there's 3 carbons, 1 double bond at the number 1 position. So it is propene, E-N-E. Okay. So 2-propanol is a secondary alcohol, and it forms propene. Now, if we did a dehydration reaction which is not symmetrical, which means it could fold either way. So we take the OH group here. We can either go after this hydrogen here or one of the hydrogens here. Again, it has to be on an adjacent carbon. So if our bonds fold, we remove the OH group, we form a double bond there, and when that hydrogen goes away there, or if we go this way, it'll form to this side. Right? So this is one side going to the right. I'm going to the left of it, and this is going to the right of it. Okay. Now we do elimination reactions. Okay. It's the carbon, it's the number of alkyl groups is going to be the major product. The one with the most alkyl groups attached to the double bond carbon is going to be the major product. Remember, carbon likes carbon for elimination reactions. So here's the carbon of the alkyl group, and you have one carbon alkyl group here and a group here, and then a group here attached. So there's 3 alkyl groups attached to the carbon of the double bonds. Okay. On this one here, you have an alkyl group attached. You have a hydrogen, then an alkyl group attached here, and one here. So there's 2. So this is your major product because there's 3 alkyl groups, R groups, carbon groups attached to the carbons of the double bond. And for elimination, carbon likes to be with carbon. So the more alkyl groups you have, the more that product's going to form. So that's your major product. Now we got to name everything. What's the name of the alcohol? How many carbons? 1, 2, 3, 4, 5, 6 carbons, right? So it's hex. All the single bonds, ol. And the O's at the 1, where do we at? 1, 2, 3, 1, 2, 3 position. 3 hexanol. And we have a methyl group at number 4. So 4 methyl, 3 hexanol. Is it a primary, secondary, or tertiary alcohol? What would it be?
Secondary.
Secondary. Secondary alcohol. And the minor product. What's the name of the minor product?
Hexane.
No, the number is going to change. Be careful when we do it because the bond went the other direction now. Okay, so the minor product is going to be 2 hexene because there's a double bond there. 1, 2, 3, 4, 5, 6 still. And there's going to be 1, 2, 3, a methyl group at number 4. So 4 methyl, 2 hexene. Okay, the major product, okay, is going to be what? Be careful because it's going to change again.
3 methyl, 3 hexene.
Perfect, perfect. It's going to be 3 methyl, 3 hexene. Okay, because you're going to count from this side now. Because you get the double bond, the lowest number, which is going to be 3 either way, but now you got a substituent group. So if it's a tie, that breaks the tie. So you count from the other side now. Okay. Let's put these up. So 4 methyl, as you can see a little bit better when it's written on the computer. 4 methyl, 3 hexanol is an alcohol, and it's a secondary alcohol. The major product is 3 methyl, 3 hexene. The minor product is 4 methyl, 2 hexene. Okay. The reason it's the major product is it has more alkyl groups attached to the carbons of the double bond. Okay. All right. Again, elimination reaction, dehydration. We're going to take the OH and adjacent carbon. We're going to take one of the hydrogens off. Does it matter which carbon we use to take the hydrogen off of?
No.
No,
No.
right, it doesn't. Makes no difference. It's completely symmetrical. No matter what hydrogen you take off, it's going to be the exact same thing. So we're all going to have one product formed. And this is going to, the electrons from the OH group are going to come down here And the ones from the hydrogen, I really are the wrong direction. The OH group's going to come down to this one, and the hydrogen going to come down to form our double bond. Okay, that one goes away. Okay, so we have our double bond formed to form an alkene. So what's the name of the alcohol? Okay, 3 carbons. The OH group at number 2, and a methyl group at number 2. So 2 methyl, 2 propanol, OL. Okay, is the alcohol a primary, a secondary, or a tertiary alcohol?
Tertiary.
Tertiary. Perfect. Good. Okay, because the carbon with the OH group has 3 carbons attached to it. Okay, and our product again is 2 carbons, and there's a double bond, so and there's a methyl group attached. So 2 methyl, 1, and then 3 carbons is pro, E and E is a double bond, propene. Okay, so the product's name was 2-methyl-2-propanol. It's kind of written a little clear, you can see it here. And it is a tertiary alcohol, like we said. The product is 2-methylpropene or 2-methyl-1-propene. Make with a double bond, it's on that one. It can only be in the one position. Okay. All right. Explain why a tertiary alcohol cannot undergo oxidation. So a tertiary alcohol has an R, C, R, R double prime, OH. There's a tertiary alcohol. Oxidation. No reaction. Cannot happen. Why?
Because it's full. The bonds are full.
Yeah, it is completely full. You're right. But why? What is it missing?
There's not enough hydrogen.
Perfect. It's completely full with R group, so there's no hydrogen to get it. In other words, you take the OH group, you take this off, and then for an oxidation, you have to take the hydrogen, another hydrogen from the same carbon. And there is no hydrogen on this carbon. So it can't undergo oxidation. There's no hydrogen atom attached to the carbonyl carbon. Can't happen. Here, I'll clear that so you can see it a little bit. Sometimes I write where the words are. Okay. No hydrogen atom attached to the carbonyl carbon, the carbon with the OH group. So you cannot have oxidation. It is a primary alcohol. It oxidizes to what? So primary alcohols oxidize to?
An aldehyde.
Aldehyde. Perfect. Secondary alcohols oxidize to?
Ketones.
Ketone. And the primary and tertiary alcohols do not oxidize. Perfect. You got it. That's exactly why. There's no hydrogen attached to the carbonyl carbon. So it can't proceed. It needs that other hydrogen to form water. Okay. So ethanol is metabolized in the liver. It's oxidized to ethanol. Remember, primary alcohol, ethanol is a primary alcohol. It goes to an aldehyde. 2 carbons to ethanol. So ethanol is not what causes the problem with alcohol. If too much ethanol is present in the body, an overabundance of ethanol is formed when the liver, because the liver performs oxidation to break down ethanol. Okay, this causes the adverse effects of your morning after hangover. So it's not the ethanol causing the hangover. Okay, it's the oxidation of it to ethanol. Ethanol is one that causes the hangover, causes all the side effects of it. Okay, continued oxidation of ethanol produces ethanoic acid. So we're continuing to oxidize it. In other words, if you have ethanol, CH3, CH2, OH, and now we went to the aldehyde, CH3, C double bond OH. And then we're going to, that's really not really clear, okay? Then you go to the carboxylic acid form of it. You add another oxygen to it. Okay, those are all steps in oxidation which occur in the liver. So continued oxidation of the ethanol, the aldehyde, produces ethanoic acid, which is this step. We've added more oxygen to it. Okay, uses the energy to destroy the cell and eventually oxidize to carbon dioxide and water. When you drink a lot, what do you have to do a lot? You got to get rid of all that product, right? It's producing water. As the liver is oxidizing the ethanol, it finally goes to CO2 and water. So you're producing a lot of water. The more ethanol you drink, the more water you're going to produce. So you got to relieve yourself a lot more when you do a lot of drinking. Okay. These reactions are catalyzed by liver enzymes. So ethanol goes to ethanal, goes to ethanoic acid, and that breaks down, giving energy to carbon dioxide and water. Okay. Here's what it looks like. This is ethanol. This is your alcohol, primary alcohol, goes to a aldehyde. This is all oxidation, and it occurs by enzymes in your liver. Oxidation of ethanol produces ethanoic acid, okay, which means you added just another oxygen in between there. Okay, we've added more oxygen, which is oxidation. And again, we haven't gotten into carboxylic acid yet, but we will. And then this breaks down to form energy and produce CO2 and water. Okay, so oxidation reduction in living systems, what we're talking about. Oxidation is the loss of electrons. Remember, it's increasing amount of oxygen, losing electrons, or increasing the number of bonds to oxygen. Okay, reduction is the exact opposite. Reduction is the gaining of electrons. Okay, so oxidation is adding oxygen in our organic systems that we usually do. Reduction is adding hydrogen. Okay, by definition, oxidation is the loss of electrons. Reduction is the gain of electrons. In organic chemistry, we could follow the electrons with like copper sulfate and things as they switched around. In biological systems, it's hard to follow the electrons. Okay, so we usually add oxygen, shows oxidation. Adding hydrogen is reduction. Okay, they're easily detected in inorganic systems because we have charged ions. We can easily follow that. Okay, organic systems are a lot more difficult. Okay, to tell what oxidation has taken place. There might be no change in charge at all, which is a lot of times the case. Okay, so an oxidation reduction occurs in an inorganic compound. The process is accompanied by a change in charge because you're moving electrons, which is electricity. It's charges, and that you're transferring electrons from one to another. Like silver breaks down to Ag plus an electron. Okay, so this has lost an electron. It's been oxidized. We can follow the electrons in inorganic systems. Okay, bromine has gained an electron. That's been reduced. Again, you can see the electrons because we can see the charges that occur and we can follow it. So in inorganic systems, it's easy to follow electrons. In biological systems, it's not quite that easy. Okay. With the loss of an electron, the neutral atom is converted to a positive ion, oxidation. Okay, you've lost an electron. That's oxidation. The gain of electron. Okay, this is reduction. Okay, you've gained an electron to form a charge. You can follow the charges in inorganic systems. Easy to tell. That's kind of out of order there, but that's okay. So organic oxidation reduction, inorganic organisms. Organic systems, changes may be tracked. Oxidation, gain of oxygen. Okay, it's easier to see in an organic system the gaining of oxygen or the loss of hydrogen. One of those two. Reduction is the gaining of hydrogen or the loss of oxygen. Okay, this is how we follow it in organic systems. Okay, oxidation is plus O2, reduction is plus H2. Oxidation can also be the loss of hydrogen. Reduction can also be the loss of oxygen. Oxygen and hydrogen work together, and that's how we track it down. Okay, this is how we look at things. This is how we determine oxidation reduction in organic organisms. Okay, we have a compound starting off here. This is an alkane. Okay, if we added oxygen to it, that's been oxidized. We've added 2 bonds to oxygen. That's been more oxidized. We've added 2 complete oxygen molecules. That's even more oxidized. So we go from a hydrocarbon to an alcohol to an aldehyde to carboxylic acid. We are increasing the oxidized form. If we go backwards, carboxylic acid to an aldehyde to an alcohol to the hydrocarbon. That's more reduced form. We're losing oxygen, or we're losing attachment to it, or we're gaining hydrogen. So it's a combination of the two. Okay, so that's oxidation reduction in organic systems. Biological oxidation reduction, okay? Oxidose reductase. It's a catalyzes biological redox reactions. Redox is reduction oxidation, and they always occur together. And we have enzymes that catalyze these reactions. And oxidoreductases catalyze these redox reactions. And we'll learn about those in the biochemical chapter. Okay, coenzymes. Organic molecules are required to donate or accept the hydrogen. Coenzyme A is used a lot with glucose, gluconeogenesis. We store glucose, we break it down for energy. It requires coenzyme A. So this donates or accepts the hydrogen to help this reaction proceed. Okay. NAD plus is also a common coenzyme. Coenzyme A, NAD plus, FADH. Again, we'll learn all about those in biochemistry as we go along. Oxidation and reduction always occur together. Remember what I said? If I use the word always, remember it, because it doesn't happen very often. Oxidation and reduction always occur together. If something's being oxidized, something else has to be reduced. If something's being reduced, something else has to be oxidized. And when we follow the glycolytic pathway, when we produce ATP, we'll learn how one coenzyme is oxidized, it causes reduction somewhere else. So we can follow it and track how the ATP are produced. Okay. Malate dehydrogenate, this is malate, this is oxalacetate. And again, your coenzyme NAD plus and then NADH, it's gained a hydrogen. So this is acting as a coenzyme to accept a hydrogen. So we're gaining hydrogen. This is being reduced. Okay. So NAD plus is being reduced. Everybody see that? It's gaining a hydrogen. You gain oxygen, it's oxidized, gain hydrogen being reduced. If this is being reduced, what does this have to be? This has to be oxidized. They always occur together. And if we look closely at it, we notice this carbon OH bond is now a carbon double bond. We've got 2 bonds to oxygen instead of 1. So we've lost a hydrogen and we've gained a bond to oxygen. So this has been oxidized. So malate has been oxidized, and NAD plus has been reduced. That's how we follow it in organic systems. Alcohol consumption, breathalyzer tests. Okay, how we determine if there's been too much alcohol consumption. What are they measuring? Oh, there we go. So ethanol, widely used as a beverage. That's what we drink, okay? Medicinal solvent, new pharmaceutical preparations. Okay. Common uses overshadows the fact that ethanol is toxic substance. Okay. Not as toxic as methanol. Methanol is extremely toxic, but ethanol is toxic to a certain degree. It does kill cells. Ethanol consumption is associated with a variety of long-term effects: cirrhosis of the liver, death of brain cells, and alcoholism. Okay. Death of brain cells is important. In my anatomy class, we go through a whole section on it. You're born with as many nerve cells as you're ever going to have. Your body cannot make brain cells. You're born with as many muscle cells as you're ever going to have. Your body cannot make more muscle cells. They can get larger. If you ever go to a gym and this trainer tells you, we're going to break down your muscles so you can build up new muscle cells, go to another trainer. They're completely wrong. You will never, if you break down a muscle cell, it never heals, ever. If you pull a muscle, that muscle's ripped for life. Okay, now you can get certain minor repairs, bleeding, scabs, things like that can help it so you can function still, but it's never going to have new muscle, just like the brain cells. Okay, you're born with as many brain cells as you're going to have. If you damage a nerve, it's damaged for life. So when you drink and you kill off, say, 2, 3, 4 brain cells, so you drink in a cup, it's a cumulative effect. Those brain cells will never regenerate. And as you get older, that's a cumulative effect. It adds on to that. So every time you kill a brain cell, you're never going to replace it. Okay. So alcohol consumed by the mother can affect the normal development of an unborn child, fetal alcohol syndrome. Okay. Fetal alcohol syndrome is a very big problem in this country. Okay. Over-the-counter cough and cold medications that were once prepared in ethanol are now manufactured alcohol-free form. Mouthwash that you use. How many people have seen Scope, Listerine with alcohol in it? Because it kills germs, right? Alcohol also causes cancer. Okay, there's 35,000 cases of oral cancer every year, and there's 2 causes. That's it. Okay, tobacco, smoking, and drink alcohol. Alcohol causes cells to malform and causes cancer to develop. Do not ever rinse your mouth with alcohol. Okay, all the studies show that if you use water, it's the same exact result. Now, with infection stuff, there's medication we can put in it, but there should be no raising your milk scene with alcohol. Okay, alcohol causes oral cancers. I wouldn't swish with it. Okay, and this is driving the influence of alcohol impairs coordination and your reflexes. Okay, at about 2 beers, 0.2% alcohol, loss of judgment, trouble doing tasks at the same time. 3 beers, reduced coordination, ability to track moving objects, difficult steering. 4 beers, trouble controlling speed, difficult processing information and reasoning. You lose reasoning. That's a real big problem if you're trying to drive. About 0.1% is roughly 5 beers. 5 beers, markedly slow reaction time, difficult staying in the lane, and difficulty braking when you have to brake. You don't analyze situations correctly. Okay, about 7 beers is 0.15%, serious difficulty controlling the car and focusing on driving. Okay, those are your blood alcohol concentrations. Okay, so short-term effects linked to the association of ethanol center its effects on behavior, reflexes, and coordination. Okay, when you start drinking, your behavior changes. Okay, start to be more open, more social. Your reflexes change, and your coordination starts to change. Okay, blood alcohol levels of 0.05 to 0.15% inhibit coordination. Okay, blood levels in excess of 0.1 are considered evidence of intoxication in most states. That's the level for a DUI. It's 0.1%. Blood alcohol levels in the range of 0.3 to 0.5 produce unconsciousness and the risk of death, alcohol toxicity. The loss of some coordination reflex is particularly serious when you attempt to drive a car. That just makes it worse. Okay. Law enforcement can rely on what's called the breathalyzer. It's a chemical analysis that tells you the concentration in your bloodstream that tells you your ethanol level. Okay. It screens for anybody's perspective of driving while intoxicated. Okay. Those with a positive breathalyzer test are given a more accurate blood test to establish guilt or evidence. Okay. Now you got to remember when they do blood tests, they're not going to do that in the street. So it's going to be several hours or so down the line. So what they're checking for is a different oxidation. Oxidation occurs at a certain rate. So they have a certain blood level of oxidation. They backtrack that according to how many hours it's been since they were pulled over. And that determines the blood alcohol level. So you see on these TV shows that they're doing blood tests and proving that the blood level is so high and it's past the time they can do it. That's not true. We know the oxidation rate of ethanol. It's been studied, we know it, and we can predict and tell what the ethanol rate or a level of ethanol was in the blood at the time that they got pulled over. So don't believe everything you see on TV. Okay? Required to exhale in a solution that will react with the unmetabolized alcohol in the breath. Okay? So it reacts with the ethanol. The partial pressure of the alcohol in the exhaled air demonstrates to be proportional to the blood alcohol level. So let you know how much alcohol is in it by how much ethanol you breathe off is partial pressure. Okay, the solution is acidic. It's a dichromate ion, which is yellow-orange. Okay, alcohol reduces the chromium ion and dichromate from a +6 to +3. The chromium ion turns green. Okay, that's how they tell. The intensity of the green color is measured on a spectrometer. Measures how dark that green color is. The darker it is, the more ethanol was oxidized. Okay, and there's your reaction. This is your acid. This is your chromate ion. This is your yellow-orange color. And this is your ethanol. Ethanol, remember, turns into ethanoic acid. Okay, in the presence of hydrogen. Remember, it oxidizes. It goes from ethanol to ethanal to ethanoic acid. And then the chromate one gets oxidized. Okay, this gets reduced. Okay, and then water is produced. And this is a green color. The darker that green color, the more of this forces the reaction in that direction. And that's how breathalyzer works. That's what they do. All right, where are we at? Phenols, we still got plenty of time. Phenols, remember what a phenol was? Phenol is a benzene ring. With an OH group on it. Used in hospitals, used for disinfectants. Phenomenal product for that. Phenols are compounds which a hydroxyl group is attached to a benzene ring, just like we drew. Okay. They're polar compounds due to the hydroxy group. The OH group is polar compound. It allows it to be polar. Simpler phenols are somewhat soluble in water. If you start getting more and more hydrocarbons attached to it, then it becomes less water soluble. You got to watch the ratio of OH groups to the hydrocarbon group. Okay. It's a component of flavorings and fragrances. It smells nice. Remember, benzene is an aromatic compound. Okay. Phenols have the formula AROH. AR stands for aromatic ring. The aromatic ring is a benzene ring. Okay. AR must be an aromatic ring like benzene. Okay. And that's what it looks like. 6 carbons and alternating double bonds, and then an OH group. The red spheres are oxygen, the black spheres are carbon, the white spheres are hydrogen. Okay, remember, that's not really what happens because this all shares and this becomes a hybrid. So this is like 1 1/3. This is 1 1/3. This is 1 1/3, 1 1/6 going around it. Okay, and it shares all those rings. Okay, the flavor of mint is thymol. Yeah, here's your phenol or your phenol compound. You add a methyl group and a isopropyl group, and that gives you the mint flavor, thymol. Okay, savory salt, carbachol. Okay, here's your phenol group. That's your phenol, and then you got attachment on both sides. Okay? It's a savory flavor. And butylated hydroxytoluene is a preservative in food. Okay, again, you see your phenol group, and you see your attachments to it. Okay, the more carbons are attached, the less water soluble it becomes. Derivatives of phenols. Okay, they're widely used in healthcare. Okay, germicides, antiseptics, disinfectants. Okay? We use it all the time in the hospitals. Okay, phenol is an antiseptic. Okay, hexachlorophene, okay, is an antiseptic. And you can see you have the benzene ring here. You have 2 benzene rings here and the OH group attached to make these the phenols. That gives it its disinfecting properties. Okay, hexachlorophene. Again, here's your phenol group, and there's a double OH group here. Okay, orthophenylphenol. Okay, now remember, we said that don't get the terms phenol and phenol mixed up. Phenol is your benzene ring attached to an OH group. Phenol is your benzene ring as an attachment. Remember, ortho was 1, 2. So this is orthophenol, and then phenol at the number 2 position. Okay, so orthophenol, phenol. And it's also an antiseptic. Okay, dilute solutions of phenols must be used in hospital settings because concentrated phenols cause severe burns. It's like a strong base. Okay, if you get on, it will burn through your skin. Okay, why are simple phenols somewhat soluble in water? Because of the OH group, hydrogen bonding. Okay, you have a polar group, you have hydrogen bonding, but the more carbons you put on it, the less water soluble it becomes. So simple phenols without a lot of carbons attached to it, the OH group is polar, so it's water soluble. The benzene ring is nonpolar. It's not water soluble. So as the hydrocarbon portion becomes larger, the water solubility decreases. So a benzene ring by itself is nonpolar, it will not dissolve in water. Put an OH group on it, it becomes a phenol, it will dissolve in water. But the more stuff you add, the less soluble it becomes. Okay, it all depends on the ratio of the OH groups to the rest of the hydrocarbons attached. Okay, what is carbolic acid and how did Joseph Lister use carbolic acid? Okay, carbolic acid is phenol. It used to be called carbolic acid, same thing. Okay, use phenol as an antiseptic and disinfectant to decrease the amount of post-surgical infections. Okay, this is in the, I think at the late 1800s, if I remember right. Use it to wash surgical instruments and sterilize his instruments. Okay. That was a big jump back then to realize that were infections and they were germs. I mean, things change an awful lot as you're doing in medicine, as you all know. Okay. Phenol reactivity. How do phenols react? Phenols are acidic. They have an H group on them, but not as acidic as carboxylic acids. Carboxylic acids are a weak acid, and the phenols are even weaker than that. Okay, because that delocalized ring of electrons help to stabilize it. Okay, they react with sodium hydroxide to give us salt and water. Remember, an acid and a base gives you a salt and water. Remember that from Chem 3. Let's take an acid, hydrochloric acid, HCl, plus base, NaOH, gives you NaCl plus water. That's a hydrogen. Okay, so when you react acid and a base, it's called a neutralization reaction because it produces a table, this is table salt, sodium chloride, and water. So when any acid reacts with NaOH, it gives salt and water. It neutralizes it. Okay, so here's your phenol, and this is NaOH. Remember, Na is Na plus, OH minus. Okay, this H is going to be kicked off because it's an acid, and it's going to form with the OH, and the Na plus is going to be with the phenol. So you get your conjugated form here with the Na plus, and you get water. You get your salt and water. Okay. Ethers. Okay. Ethers have the formula ROR. Okay. So we have a function group. Say we have CH3, O, CH3. That is an ether. Has an oxygen in the center, 2 R groups on either side. Okay. R can be aliphatic, which is our normal hydrocarbons, or it can be aromatic. It can be a benzene ring. It can be either one. Ethers are slightly polar because it's a little bit of a polar bond between carbon and oxygen here. Oxygen's a little more polar. It's going to pull electrons towards it, so it's going to be a little bit negative. It's going to be a little bit positive. Not as much as alcohols, not as much as carboxylic acids, okay, not as much as aldehydes, but a little bit because they're trapped between these 2 carbon things. So you have a little bit of polarity. So they're slightly polar due to that carbon-oxygen bond. They do not hydrogen bond. Remember, the definition of hydrogen bond is hydrogen atom has to be directly connected to a very, very small, highly electronegative atom, like fluorine, oxygen, nitrogen. So if you draw this out, you have your oxygen, you have carbon, Are any of those hydrogens directly connected to the oxygen? No. So you're not going to get hydrogen bonding. For hydrogen bonding to occur, the hydrogen has to be directly connected to the oxygen or the nitrogen atom. Then you have hydrogen bonding. But it's not connected to it. There is no way you're going to have hydrogen bonding. Okay? Because a hydrogen is not connected directly to the oxygen there. Okay, and this is the same as this is a CH3. There's your carbon, 3 hydrogens, carbon, 3 hydrogens attached to your oxygen molecule. Like I said, there's a slightly difference in electronegativity between oxygen and carbon. So these are going to pull electrons towards the oxygen, giving it a little bit of a negative charge, but not much. So it makes it slightly soluble in water. It's slightly polar. Physical properties of ethers. Okay, they have much lower boiling points than alcohols because they do not have hydrogen bonding. They don't have that force holding them together. But they're higher than hydrocarbons, which don't have any oxygen at all, because we have that little bit of oxygen there pulling those electrons, giving you a little bit of polarity stick together. So if you're looking at boiling points or melting points, the boiling points are lower than an alcohol, but higher than a hydrocarbon. Okay, so this is a hydrocarbon. This is our ether, and this is an alcohol. This is the highest boiling point. This is the lowest boiling point. As we work across from side to side. So you have butane, you have methoxyethane. We'll talk about naming those in just a second here. Or you got ethyl methyl ether. That's how we do it. This is an ether. There's an ethyl group on one side, and there's a methyl group on one side. Okay, and you got propanol, which is propyl alcohol. Molecular weight is 58, 60, and 60. So about they weigh about the same. So they're roughly the same size. So we're comparing apples to apples. Boiling point is negative 0.5, 7.9, and then 97.2. You see how this one jumps up really high because of hydrogen bonding. This one goes from negative 0.5 to 7.9. So it's up a little bit, not a real big jump, but it's a little bit more than a hydrocarbon because of the difference in electronegativity with the oxygen in between those two carbon groups. Okay. Common ether names. Common names you might see for ethers consist of names of the two groups attached to the oxygen, and you list them in alphabetical order or size, followed by ether. Okay. There's no real rule people follow. People do it different ways. Sometimes they put in alphabetical order, some do it by size. Either way is fine with me if you're going to do the common names. Most of the stuff's going to be on the IUPAC name, which is a little bit different because that there's no confusion on. You can put it either way. Each of the three parts is a separate word. We don't run the words together like we did on the IUPAC system. Okay. Name each of the following common names. Here's our ether. Okay. One side is what?
A methyl group.
That's a methyl group. Other side is isopropyl group. And you put it by size, by alphabetical order, whatever you want. So it could be methyl, isopropyl ether. Or it could be isopropyl methyl ether. Okay. So isopropyl methyl ether or methyl 2-propyl ether. Okay. So this is methyl. This is 2-propyl. Okay. It's attached to number 2 carbon. So however you want to do it is fine. Okay. This one here, this is an ether. We have this group attached and we have this group attached. What do we call this thing when it's an attachment? It's not phenol anymore. It's what?
Phenol.
Phenol. When we have it as an attachment, it's a phenol group. So this is ethyl, phenol, ether. Okay. And again, by size or alphabetical order, it's the same either way. That it comes out the same this way. Ethyl, phenol, ether. Okay. What would that be called? How many methyl groups do you have?
Dimethyl ether.
Perfect. Dimethyl ether. There's 2 methyl groups. You got it. Take a guess on that one.
Ethyl methyl ether.
You got it. Perfect. Ethyl methyl ether. There's an ethyl group, 2 carbons. There's a methyl group, and this thing is an ether, oxygen center. That's how to do common names. Okay. This is ethyl. And this is CH. So what would that would be 2-propyl. 2 CH3 groups on there. Okay. So ethyl 2-propyl ether or ethyl isopropyl ether, however you want to do it. It's an isopropyl group or it's a 2-propyl. And there's 3 carbons and attached to the second one. So 2-propyl. That's how they get it. Okay. IUPAC name. This is a little more used because there's specific rules with this one. All right. IUPAC names are based on the alkane name of the longest chain attached to the oxygen. Just like we've done before. The shorter chain is named as an oxy. So it's, if there's one carbon, is a short one, it's methoxy. If there's two carbons, it's ethoxy. Three carbons is propoxy. Okay. The alkane and A and E is replaced by OXY. So you drop the name A and E and you replace with OXY. So that's ethoxy attachment right there. Okay, so that's the shorter of the two chains. So here we have two chains. Here's your oxygen, it's an ether. We have 1, 2, 3, 4, 5 carbons here and 1 carbon here. What's the shortest chain? The 1 carbon. So that's a methoxy. Okay, so the name is methoxy, and we put the other chain as pentane. So we take the shorter chain, which is this one here. Okay, and we combine, we drop the A and E ending and replace it with OXY. So it becomes methoxy. And then we add the longer chain as its regular name, pentane. So methoxy pentane. Okay, name this guy. We have an attachment here and an attachment here. And how many carbons is this? 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So this is 1 carbon. We all know that's methyl. 9 carbons is no name. Okay, all single bonds. So how would you name this? There's to be methoxy. That's your shorter chain. And then this is attached to the number 3 carbon. 3, no name. So methoxy, 3, no name. The shorter one is given the oxy, drop the A and E and add oxy. And then you give the name that you normally would. The attachment occurs at the number 3 carbon. So 3, no name. All right, here we go again. You look at, you analyze, you see this as an ether because it's an oxy inside by 2 R groups. We have a 2 carbon chain. We have a 3 carbon chain. So how would you name this? What would the first name be?
Ethoxy.
Eth, perfect. Oxy. What would the second name be? Three carbons.
Propane.
Propane.
Propane, perfect. All single bonds. Ethoxy propane. Why is it not advancing? Oh, there we go. Might hit too many spaces. All right. Again, that's an ether. This is one side. This is the other side. This side has 1. This side has 3. Which one's shorter? Number 1. So what's the first part of the name now with 1 carbon?
Methoxy.
Methoxy. What's the second part of the name?
Propane.
Propane. You got it. That's all there is to naming ethers. Methoxy propane. Okay. Again, there's 2 carbons and there's 1, 2, 3, 4, 5 carbons. So the first part of the name is eth because there's 2 carbons. Ethoxy. And then they want to say 1, 2, 3, 4, 5 pentane. Ethoxy, let me move that out of the way. We don't have to include all that. Ethoxy pentane. This is a shorter chain. You drop the A and E and add oxy to the end of it. And this tells you how many carbons there are. And then you name the last one just as you would as a hydrocarbon. Nice. Keep hitting spaces here. All right. So now we've got one side and another side. We have 3 carbons over here. We have 1, 2, 3, 4 carbons over here. So how do we name that one?
Propoxy butane.
You got it. Perfect. Propoxy butane. Propoxy is the shorter chain. Prop, you drop the A and E and add OXY. And then we name the hydrocarbon as we normally would with the number of carbons that are attached to it. Propoxy butane. Okay. How ethers react. Okay. Ethers are relatively inert. They are very difficult to react. Okay. Do not normally react with reducing agents or bases. Okay. They're very volatile. They're very explosive. Okay. Highly flammable. They're easily oxidized in air. Okay. Symmetrical ethers may be prepared by dehydrating two alcohol molecules together. So to make it, it requires a heat and an acid catalyst to occur. So we take two alcohol molecules. We have ROH, ROH, and we're going to do a dehydration reaction between those two. So we're going to remove an OH group from here and an H group from here. So this R is going to attach to that oxygen. And we've lost water, a dehydration reaction. A lot of times we see dehydration reaction because water is very stable. It's easy to produce that reaction because we're going to an extremely stable compound. Okay, so we're taking an OH from one, an H from the other, and pressing them together. And that's how we make an ether. Okay, so ethanol. Ethanol combines with itself. Again, we have CH3, CH2, OH. Okay, we drop the OH from one. We drop the H from the other. That gives you water when those combine. And then this combines with this, right where that bond was. So O, CH2, CH3. So ethoxyethane. Okay. Right equation showing the synthesis of dimethyl ether. So we're going to make dimethyl ether. Dimethyl ether is that methyl groups on both sides. Now the IUPAC name for that would be methoxymethane. I know they're both the same size, just pick one then. So methoxymethane is the IUPAC name. How are we going to make it? We're going to use an alcohol that looks like that with an OH, right? So we're going to take methanol and add another one. Okay. And we're going to take an OH group and a hydrogen to form water. Okay. And then we're going to get CH3O and CH3. That's dimethyl ether. That's how you make it. Two alcohols. And remember, we're going to take an OH from one and an H from the other to give you water. So now you got CH3O and you got CH3. So that just combines there. And you get dimethyl ether or methoxymethane and water. Right equation of the dehydration reaction that would produce diethyl ether. Again, diethyl ether is ethoxyethane, and it's two carbons on each side. So you want to produce this guy right here, diethyl ether, two ethyl groups. So tell me what alcohol you would start with. How many carbons would the alcohol have? It would have two.
Ethanol.
Perfect. Ethanol. You got it. You would have ethanol, CH3, CH2, OH, and you know another methanol. You combine with two of them, CH2. Again, I'll write it down with equations like that, OH. So what we're going to do is take a hydrogen from one and an OH group from the other. That gives us water. And it's going to give us CH3, CH2O with a CH2, CH3 attached to it. CH3, CH2O, and CH2, CH3. That's how it's made. That's your diethyl ether. or your ethoxy. If we get rid of that water group down the bottom there. There you go. All right. So we've got ethanol and ethanol, 2 ethanol molecules have to combine. And again, we take an OH group off of one and an H group off the other. So then this connects directly to there with lots of OH group. And you get diethyl ether. Two molecules of 2-propanol. Okay. 2-propanol, propane is 3 carbons. 2-propanol, and the OL group is on the number 2 alcohol. Okay, that's a CH group right there. And it takes 2 of them. That's a really lousy drawing. Hold on. We can do better than that. All right, so propanol, CH3, CH, OH, CH3. And a second one, CH3, CHOH, CH3. All right. Presence of a strong acid, you get dehydration reaction, you're going to lose water. So we're going to lose an OH from one and an H from the other. So we're going to connect them. We're going to have CH3, CH, CH3, and that's we have left to connect, right? That's this structure right here. And it's connect to this oxygen where the hydrogen was gone to oxygen. And that's connect to CH, CH3, CH3. Okay. And that's how it connects. So this could be isopropyl, diisopropyl ether. There's an isopropyl group on both sides. Okay, so 2-propanol and 2-propanol, diisopropyl ether, okay, or di-2-propyl ether, where the propyl group is connected to the second one. Either one of those is acceptable. Okay, but it just shows how the ether is connected to the second carbon of the chain on both sides.